Have you ever wondered how complex numbers breathe life into the realm of polynomial exponentiation? They do this by playing a vital role in techniques such as the fast Fourier transform, FFT, and its inverse, the inverse fast Fourier transform, FFT. Let's delve deeper into this fascinating world. To start, let's discuss the roots of unity. These are complex numbers that, when raised to a certain power, equal 1. Complex numbers offer a natural representation for these roots, which are essential in polynomial evaluation and interpolation. Think of them as the building blocks of our polynomial world. Moving on, we encounter the fast Fourier transform, or FFT. This algorithm efficiently computes the discrete Fourier transform DFT of a sequence, transforming a polynomial from its coefficient representation to its value representation. This means it evaluates the polynomial at the roots of unity. The real beauty of the FFT lies in how it uses the symmetry and periodicity properties of these roots to drastically reduce computational complexity. Instead of a cumbersome, time-consuming quadratic process, it becomes a more manageable logarithmic one, making it a real time saver when dealing with high-degree polynomials. Next up, we have complex exponentiation. Thanks to complex numbers, we can express complex roots of unity as powers of e, the base of the natural logarithm. This link between complex numbers and exponential functions paves the way for efficient computation of powers of complex roots, a cornerstone in polynomial exponentiation. Once we've transformed our polynomial into value representation using the FFT, we can move on to polynomial multiplication. This process becomes a straightforward pointwise multiplication of the transformed polynomials. Why, you ask? It's because convolution in the coefficient domain becomes pointwise multiplication in the value domain, a task that can be handled efficiently using the FFT. Finally, after performing pointwise multiplication in the value domain, we employ the inverse fast Fourier transform, or IFFT, to transform the result back into the coefficient representation. This gives us the product of the two polynomials. In conclusion, complex numbers are the unsung heroes of polynomial exponentiation. They provide a natural representation for roots of unity, enable efficient transformation between coefficient and value representations with the FFT and IFFT, and simplify polynomial multiplication in the value domain. Thanks to them, even polynomials with large degrees can be tackled efficiently, making the daunting task of polynomial exponentiation far more achievable.